I think that'll work. Okay, this quality is gonna suck. That's okay. Or I don't know if it's okay, but it's the best I can do. All right, I'll turn the lights back on. Okay, so matrix stuff. Let's go. That's why I write things on the board. So matrix fundamentals. Matrix fundamentals. Okay. We've talked about some of this. So a matrix has rows and it has columns. Okay. For shorthand, I'm going to use M to denote the rows of a matrix. I'm going to denote N to denote the columns of a matrix. Okay. So we can talk about some 3 by 1 matrix, which means that it has 3 rows and 1 column, right? Sometimes we just call this a column vector, okay? But vectors are matrices. They're just matrices that only have one of the constituent elements, right? And however many of the other they want, okay? So this is a column vector, okay? In this case, right? We can also have a row vector, right? Right. So this is a 1 by 3 matrix, right? A row vector, right? We might as well introduce this word now, conformable. Conformable. Okay. We will talk about what this means in more detail when we get into multiplication. Sorry, I'm seeing if I can make this capture just a little bit more on the screen. Okay. So in order for 2 matrices, which includes vectors, in order for 2 matrices to be conformable, the matrix on the left must have the same number of columns as the number of rows on the right. Okay, we'll get back to that in just a minute, okay, but I might as well say it since I have those 2 next to each other. Okay. So let's just start with matrix addition and matrix subtraction. Let's see. I thought that I did. If not, I'll mess it up. That's fun. Just a second. Okay. Okay. So for addition or subtraction, for addition and subtraction, for addition and subtraction, in order for so if I want to take so let's say that I have some matrix A, so that A, B, A, M by N matrix. Okay. In order for A minus B to exist, say exist, B must also be a M by N matrix. Okay. This is true for both addition and subtraction. I wrote subtraction there, but this is also true for addition, right? In order for A minus B to exist or A plus B to exist, then B must also be a M by N matrix. So this is how addition and subtraction work in matrices, right? So let's just pick, I thought that I had an example, but I must not. I brought the other sheet, so I'll just make one up and that'll be fine. Okay, so let's have some simple matrices. Let's let A be equal to, this blue is a little smudgy. Let's let A be equal to 1, 2, 3, 4. Okay. And let's let B be equal to 1, 1, 3, 1. Just picking numbers out of a hat. Okay? These are each 2 by 2 matrices. Agreed? Okay? So it fits this property, right? The number of rows in A is equal to the number of rows in B. The number of columns in A is equal to the number of columns in B. Right? For addition and subtraction to work, that must be true. That must be true. So for me to take A minus B, everything is element-wise. Everything is element-wise. 1 gets subtracted from 1. 1 minus 1. Okay. 2 gets subtracted by 1. 2 minus 1. 3 gets subtracted by 3. 3 minus 3. And 4 gets subtracted by 1. 4 minus 1. Okay. Such that the resulting matrix is 0, 1, 0, 1. Or 3, sorry. Everybody cool with that? Okay. So addition is pretty straightforward. Okay. All right. Let's talk about something a little bit more complicated. Subtraction, addition, right? Just two sides of the same coin. Both work fine in matrices. Let's talk about matrix multiplication. Matrix multiplication. I know I have examples of this one. Maybe not good examples. That is not a good example, Joseph. All right. Well, we'll make one for that too. I'll see that. So let's just suppose, let's stick with what we have here. Actually, we can do this. We can do this more fun. Let's work with a row vector. Let's work with a row vector of, say, 1, 0, 1. Let's work with letters first. A, B, and C. Okay. Let's work with a column vector of D, E, and F. Okay. I'm using symbols here. To make just an illustrative point, as you guys will see. Okay, but these could stand for any kind of number. Okay, any real number. Okay. What are the dimensions of this left matrix?
Be 1 by 3.
You got it. This is a 1 by 3. Okay. What are the dimensions of this matrix? 3 by 1. 3 by 1. Okay. These are conformable matrices. Right? The number of columns, on the left is equal to the number of rows on the right. Okay. Conformable matrices can be multiplied. Non-conformable matrices cannot. Okay. So if this is A, right, I'll just write it up top. If this is A and this is B, then A times B is defined. A times B is defined because they are conformable. Okay, crash course. I'm not going to write it on the board, but we're with me, right? This is what A times B is equal to. A times B will be a matrix, right? We know it's conformable. It will be a matrix with the number of rows equal to the matrix on the left, and the number of columns equal to the number of columns on the right. We will get a 1 by 1 matrix. Okay, this is called a dot product. Okay, there's actually a trigonometric interpretation of this, which we won't get into today, but it's kind of neat, right? We can think of vectors, if anybody's ever taken physics, we can think of vectors as sort of like these little lines in space, right? They have both direction and magnitude. Okay, well, if these are things in space, then there should be some way to measure the angle between them. Okay? Dot products do that. Okay? Dot products give you, there's a bit more to it, but dot products basically give you the cosine between two vectors. That's one of the things that they give you. Again, I'm not going to get into that today. I'm just letting you know that in addition to all the things we'll use them for, there is that property. Okay? It's pretty neat. It's pretty neat. But for our sake, we know that our result is going to be a 1 by 1 matrix. We know that. Okay? So here's how it works. Anytime you are multiplying, I think I meant to throw that marker away earlier today. Anytime you are multiplying two matrices, your first element will be equal to the dot product of the first row with the first column. Here, because there is only one row and one column, that's the entire result. Here's what a dot product is. It says take the first element of your row vector, right, A, and multiply it by the first element of your column vector, D. Add to that the second element of your row vector, B. Multiply that by the second element of your column vector, E, right? Third element, C, multiplied by third element, F. Okay? That answer is your answer. That is the result. That is what A times B is. Cool with that? Okay. That's why it's what we call a scalar, another term that I'm throwing at you. A scalar is a matrix that is 1 by 1. In other words, it's all the numbers you're used to. It's all the numbers you're used to. Okay. It's something that doesn't have dimensions. Okay. Just a 1 by 1. It's a scalar. The dot product is a scalar. Okay. Matrix multiplication does not commute. Matrix multiplication does not commute. The product of A times B is not the same thing necessarily as the product of B times A. We are about to demonstrate that with alarming clarity. Okay? We just saw that this is a scalar, right? A single thing is what you get out of this, agreed? Right? A matrix that is a 1 by 1, right? 1 by 1. Observe what would happen if instead we tried to take B times A. We tried to take B times A, right? Okay, now I have D, E, and F, right? That is a 3 by 1, agreed? Multiplied by A, B, C, which is a 1 by 3. Are they conformable?
No.
Are you sure? What does conformable mean?
Yes, the column and the rows have to be the same.
Yes. The columns of the matrix on the left must be equal to the number of rows on the matrix on the right. So they are conformable. But now, what will our result be?
3 by 3.
Our result is going to be a 3 by 3. Just from that alone, we know that our result is going to be wildly different from what we got here. Agreed? So let's take a look at what that looks like. We know that it's going to be a 3 by 3. So let's make ourselves some space. Okay. Call this thing BA, because that's what it is. Okay. So our very first element, just like we had here, is going to be the very first element of the row vector, right? This is our row vector of the matrix on the left, times the very first element of the column vector from the thing on the right. Pretty boring, so it's just D times A. Okay. The second element in the first row is going to be equal to the first row vector times the second column vector. So that's going to be D times B. Okay. And the third, we will get more practice with multiplication because this isn't clicking. The third is also going to be D, but now it's going to be times C. Now it's going to be times C. People with me? Okay. All right. So moving forward, right, now we're going to go on. We're going to have E times A, then E times B, then E times C, right? E times A, E times B, E times C, right? And we're going to have F times A, F times B, F times C. Very, very different than the other matrix. Okay. Matrix multiplication does not commute, generally. There are special matrices that do. There are special matrices that do. Okay. Let me find this really quick for the next thing. Okay. Questions so far? Okay. Before I move any further, yeah, we still have that. Before I move any further, let's make sure this is still recording. Let's talk about the transpose of a matrix. It's actually pretty straightforward. Okay. The transpose of a matrix just means take the rows and turn them into columns, take the columns and turn them into rows. Okay, that's literally what it means. So if and I'll usually denote it like this. I'll put a little T on top of B. You'll see different books use different notation. This is the one that I like the most. Okay, so if this is B down here, right? I take the first row vector, and that becomes the first column vector, right? So if this is the B that I'm working with, B transpose would be 1, 1, okay? And then the second row vector becomes the second column vector, 3, 1. Okay, that is the transpose of B. I know that I have some stuff on that too. So far, I haven't enjoyed the prep that I actually did when I wrote that. So far, that. No. Transpose. Oh yeah, this is a good way to think about it, right? So the ith, jth element, of the original matrix, becomes the j ith element of the transpose, right? Sorry, I'm out of letters there. Transpose of the transpose. Okay. Just a fancy way of saying that you exchange the rows and the columns, right? So maybe this is easiest to see. We'll just do another example. So say I have some matrix that is A, B, C, D, E, F, G, H, I. Thanks, English. Okay. The transpose of that thing is equal to, okay. So as I said, the ith, jth element of the original matrix becomes the jth, ith element of the transpose, okay. This is the one element, so it'll become the one element. No change to that one. This is the first, right? Second, first element, right? Rows and then columns. So this is the I is equal to 2, J is equal to 1 element. Okay, it will become the J is equal to 1,
Wait,
I is equal to 2, right? Did I do that right?
The I is equal to 1.
Yeah, let me write it out, sorry. Here I is equal to 1, J is equal to 2,
Mhm.
right? So when I flip that over here, right, the, let me see if I wrote this right. Here, oh, well, that's because I wrote it wrong here, sorry. Yeah, maybe that's what you were saying, Josh.
Yeah.
Two,
This
one.
is the I is equal to 2, J is equal to 1 element. I was trying, my brain was working faster than my hand. Okay, so over here, it'll be the element, right? It'll be the element where its row position,
Is it-
is 1, right? And its column position is 2.
Mhm.
Does that make sense?
Yeah.
Right, so here, J is indexing the rows, I is indexing the columns. In the original, I was indexing the rows and J was indexing the columns. Okay, so this element goes here. Okay, this element, right, you can do this for any of them. This element has an I is equal to this element here, G.
I is still 1.
I is still 1. Okay,
Oh, for the transpose or for the original?
for the original.
Oh, then
Okay.
I is 3.
Yeah, okay, thank you. I is equal to 3 and J is equal to 1, right? So in the result, the row, which here is indexed by J, sorry, that's confusing, but the row will be 1 and the column will be 3. With me on that? Right, so G must go there, right? This is the more formal way to do it, right? But it suffices to remember that each row vector here becomes a column vector, right? So our first column vector is going to be A, B, C. Our second column vector is going to be D, E, F.
Mhm.
And our third column vector is going to be G, H, I. Okay? That is the definition of a transpose. With me?
Yeah.
All right, you guys are doing great. Linear algebra crash course. Let's go. Okay. So we've talked about matrix addition. We've talked about matrix subtraction. We've talked about conformable arrays. We've talked about matrix multiplication at least a little bit. I definitely want to do more on that, but we have. And then we've talked about transpose. Yeah. What are arrays? Yeah. All right. So let's pick a matrix out of a hat that will be just slightly harder. Okay. So let's do A, B, C, D. And we'll multiply it by E, F, G, H. Right? So this is a 2 by 2, and this is a 2 by 2, agreed?
Mhm.
Okay, are they conformable?
Yes.
Yeah, so their product is defined, right? So this multiplication will be equal to A, sorry, for the very first element, it'll be equal to A multiplied by E plus B multiplied by G. Okay. That is the very first element of the resulting matrix. Okay, I went along the row vector of this and down the column vector of that, just like I did over there with the dot product. Okay, the only difference here is that now I have multiple elements. I have multiple elements in that row vector and multiple elements in that column vector. With me?
Yeah.
Okay. The second element, or the first row, second column, is going to be equal to A multiplied by F plus B multiplied by H. Okay. People with me?
Mhm.
First row, second column, right? First row, second column. Okay. Now we're going to take this row, multiply it by this column, right? So we get C multiplied by E plus D multiplied by G, right?
Mhm.
And now we're going to get this row multiplied by this column, right? So we get C multiplied by F plus D multiplied by H. That is the resulting matrix.
Mhm.
And that is the resulting matrix. Questions?
No, I'm just seeing, looking at it,
No, makes
remembering the pattern, this, the first column of the second one remains in both all the values of the first column of the new
Yep.
it's coming together now,
Yep.
how it all works and why we do it this way.
Absolutely. It's a lot. I'm never going to ask you to do it by hand, but I would like you to understand it. We will figure out how to do it with R. Okay? But I'd like you to understand what R is doing.
Yeah.
Okay. So we now have all the tools to talk about some headier stuff. Let's just think about, does everybody have
Yep.
this side of the board? Okay. Earlier I said that matrix division doesn't exist. I meant that. First, let's just sort of try and find an analog for a very important scalar concept that everybody knows and loves. Okay? Everybody knows this one. If I take some constant, some scalar constant, and I multiply it by 1, you know, let's write it like this just to make sure. If I multiply it by 1, what do I get?
So
I get A. Okay. There is a matrix. There is a matrix in the universe that exists such that when I multiply it, we'll call this matrix I, such that when I take I and I multiply it by some matrix A, I get A. That matrix exists. We call it the identity matrix. Okay? It is the matrix equivalent to a 1 in scalar algebra. The matrix equivalent to a 1 in scalar algebra. Make sense?
Mhm.
And it looks like this. It looks like this. 1, 0. Sorry, let's just use A over there. We'll stick with the 2 by 2 square matrices. Square matrix just means it has the same number of rows and columns. 1, 0, 0, 1. That is an identity matrix. Identity matrices have 1s along the diagonal, and 0 everywhere else. That diagonal is the left to right diagonal. If we take this and we multiply it by A, so let's use this A, B, C, D. Okay. If we take this and multiply it by A, B, C, D. Okay. Let's see what we get. Okay. I will get 1, right? I will take this first row vector. Agreed? Sorry, first, are these conformable?
Yes, they are.
Okay, right? My result will be a 2 by 2. Agreed? Okay, so this very first element here is going to be 1 multiplied by A, right? Plus 0, 0 multiplied by C. Agreed? Okay, over here, this element will be 1 multiplied by B plus 0 multiplied by D. Agreed? Okay, now we're down here. Okay, so now we have 0 multiplied by A plus 1 multiplied by C. Okay, and finally we have 0 multiplied by B plus 1 multiplied by D. Okay, so pick any value of A, B, C, and D that you like. No matter what you do to it, when you multiply it by 0, you get 0, right? So what we end up with here is A, B, C, and D, which is what we started with. Okay. So the identity matrix is the matrix equivalent of a 1 in scalar algebra. Multiplying it by the identity matrix doesn't change a thing. Okay. With that in mind, let's talk about the, I'll say, matrix division. Okay. The truth is there is no such thing as matrix division. There is, however, this. In scalar algebra, we all know that if we take A and multiply it by 1 over A, we get what? We get 1.
over A.
What?
A over A,
Which is
1.
Which is 1. there is some matrix, we'll call it A inverse, so that means A minus 1, A inverse, such that when you multiply it by A, you get the identity matrix. You get the identity matrix, right? Which is the closest thing to division you could ask for, right? I want to multiply something such that when I multiply it by that thing, I get the matrix equivalent of 1, right? That's the same thing, basically, as we were getting with our scalar stuff. Okay? This will probably be the headiest thing we talk about today. Everybody good with this?
Yeah.
Yeah, okay. 15 minutes to do it. Okay. So, all right. So, everything takes longer than I think it will. Yeah, we'll just start. So let's let A be equal to 1, 0, 0, 0, 1, 0, 0, 1, 1. Okay. There is some matrix out there. There is some matrix out there in the world that when I multiply it by A, I get the identity. 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay? That's the identity. Okay. How do I find A inverse? How do I find it? Okay. There are different methods out there in the universe. Okay. The sort of go-to, at least my favorite, is called elementary row operations. I can't spell element. Is that an A?
EN, or TAR.
Okay. Elementary row operations. Okay. These come in three forms. You can swap. You can swap two rows. You can multiply a row by a constant. Okay. Or you can multiply a row by a constant and then add it to another row. Okay. These are what elementary row operations are. Let's see how we use them in a very, very quick way. Everything in this class is quick. So we'll do something fun. Yeah, I'm gonna try this. I didn't write down the steps as well as I should have, so this doesn't go well, I apologize. Okay, so one of the things we can do with matrix algebra is solve for systems and equations. So let's say that we have some system that looks like this. 2x minus 4y is equal to 3. And we also have 3x plus y is equal to negative. We can represent this in matrix form. We can represent this in matrix form. We can realize that this is the same thing as 2, negative 4, 3, 1. Okay, multiplied by some column vector called x and y. And then that is equal to some column vector 3 minus 1. We can do that. Okay. Right? This is a 2 by 2, right? This is a 2 by 1. Okay. The result will be a 2 by 1. Okay. All right. So let's just ignore this x and y for a second here. We won't forget where they are, but we don't need them for the moment. So I have this matrix. I have this matrix with a 1 and a minus 2 and a 3 and a 1. Okay. And I have the solution. I have the solution is 3 and minus 1. Okay. This is what we call like an augmented matrix. I'm throwing way too much at you guys, which I might regret, but what I'd like to do is I'd like to perform elementary row operations. Elementary row operations. Yeah, go ahead.
Sorry, where did we get this matrix from the last one? Because those two are different.
Oh yeah, I
Okay.
performed an operation. Sorry, you're right.
That's okay. Sorry, I just wasn't.
I didn't realize that I changed it in between my notes. Better?
Thank you. I was
Yeah.
not sure. That makes sense.
So elementary row operations, right? So if I take the top row, and divide it by 2,
Mhm.
that's one of my elementary row operations, right? Multiply a row by a constant, right? If I do that, right? If I do that, I take the entire top row and multiply it by a constant. I get 1 minus 2, right? 1 minus 2, I get 3 halves, right? I haven't changed this other row, so it just comes back.
Mhm.
So that's performing the elementary row operation of taking a constant and multiplying it to
Yeah.
a certain row.
Makes sense.
All right. Then I need to follow my notes. Then I'm going to take the bottom row. I'm going to take the bottom row. I'm going to multiply it by 2, and I'm going to add it to the top row. Okay, that's another one of my elementary row operations. Okay, I'm going to take the bottom row, I'm going to multiply it by 2, and I'm going to add it to the top row. So the top row gets 6 added to 1, so 7, right? 3 added to negative 2, it's positive 1. All right, wait.
You're doubling it.
Yeah, thank you. I'm multiplying by 2. So that's 0, right? Positive 2 plus negative 2, 0. Over here, right, I have 3 halves plus a negative 2, right? So that's the same thing as negative 4 halves. Everybody fold that, negative 4 halves plus 3 halves, right? Which is what?
Negative 1 half.
And I haven't changed anything on the bottom yet. 3, 1. Okay. Okay. I'm going to take the top row and I'm going to multiply it by 3.
Okay.
Okay. So I'm going to get 21, 0. I'm going to get 3, negative 3 halves, right? Okay. Technically we do these all at one time, but because I'm running out of space, I'm going to do the same thing to the bottom row.
Okay.
Okay. I'm going to multiply that by the same, or not by the same constant. I'll multiply that one by 7. Okay. So that I get 21, 7, negative 7. Everybody with me?
Mhm.
Okay. Then, I guess I already have a line there. Then I'm going to take the bottom row. I'm going to take the bottom row
Mhm.
and, well, actually, let's just do it this way. Let's take the top row, multiply it by -1, and add it to the bottom row.
Okay.
Okay, that's one of my elementary row operations, right?
Mhm.
Okay. So I get 21, 0, -3/2 for the top, because I haven't changed any of that yet. Okay. But for the bottom row, I now have a 0, right? And 7, right? And then over here, I take +3/2, right? And I add that to -7. -7 plus 3/2. Is that cool with everybody?
Mhm.
Which, if I follow my notes, I think I get -11/2. That can't be right. Maybe it's right.
Yeah, because it's
Yeah, okay.
-14/2 plus, so you're, 14 minus 3.
Yep.
So it should be -11/2.
Okay. -11/2.
Mhm.
With me?
Yep.
Okay. Okay. Then I'm going to take my top row. I'm going to divide it by 21. I'm going to divide it by 21. Okay. I'm going to take my bottom row and I'm going to divide it by 7. Okay. Again, those are 2 steps. I'm going to write them in
Yeah.
one just to save me some word space. So I'm going to end up with 1, 0, right? I'm going to get -3/42, right? And then I'm going to get 0, 1. I'm going to get -11/14. People with me?
Mhm.
Okay. What this means is that I have a solution.
Mhm.
I have a solution. I have this solution. I have 1, 0, 0, 1 multiplied by xy is equal to -3 40 over -11 14ths.
Mhm.
Okay. In other words, x is equal to -3 40 and y is equal to -11 40. Okay. You can use this stuff, these elementary row operations, to solve for systems of equations. Pretty cool, right? It would take me too long to spin up the computer, but we can test it. We make sure my solution works, right? So if we plugged in our answers here, right? So I won't write it all out, but you guys have calculators, right?
Mhm.
So if we took 2 times -3 divided by 42 plus 4 times -11, I really hope that I'm using this calculator right, divided by 14. Yeah, my stuff's not right.
I'm trying to do it so I can.
Yeah, okay, I get 3. Okay, I just did the top one. You could have picked either one. Okay.
Mhm.
Just double checking. It's been a minute since I actually worked these examples out. Okay. The point is that we used our elementary row operations to solve for this thing. Okay. I'm closer on time than I thought I was going to be. So, what we're going to do, let's see, we're done at 15, right?
Mhm.
So I have 3 minutes. I'm going to have to pick this back up when we come back. Okay. There will be a homework assignment. I'm going to assign it on Friday since that's when the current homework is due. We don't have 2 concurrently. Sorry, you'll have homework over break. It won't be super long, but it'll involve this stuff. So the R equivalent, this is something that I want you all to know. The R equivalent of matrix multiplication is to take A and write this syntax, right? It's a percent sign, an asterisk, and another percent sign. Okay. I'll make sure to include a note with the homework. It'll make that perfectly clear. So if I want to take matrix A and multiply it by matrix B, This is what I do.
Mhm.
Okay. All right. Also, I will ask you guys the quiz questions. I'm going to stop